Hello, my name is Jason, and I am doing the Fluent Project 3, where we are simulating three different scenarios with 2D with 2D flow around a cylinder object. So, what we are going to start is by making our geometry. Here we're going to drag that icon over here. Make sure that this is 2D. Right click and open up the design modeler. We are then going to sketch on the XY plane. We are going to be sketching a circle about the origin. We're going to make this diameter 1 meter. And then we are also going to sketch a couple of lines in order to make our area that we will be having flow. So here we start off with two horizontal lines where each will be a length of 25 meters. I'm going to do that right now. So these both will be 25 meters. And then we're going to draw a vertical line that will also be 25 meters each in order to create our rectangle that will be the position for our flow. So here we're going to make these also 25 each. And then this is kind of our outline for the actual square or rectangle that we will be creating. Here's that, and then we can just come here, delete these lines, these extra lines that we don't need, and then we should have our box. And then just a circle. So now go to mode, go to our sketch, surfaces from sketch, apply it, and then generate. So now we have this and a little bit of a circular hole in the middle. We can then close this tab out and then open up our mesh and then create a mesh. So for our mesh, it's going to load our geometry very soon. Here it is. And what we are going to start with is click on our mesh, right click, we're going to insert a method where we're going to click on this face, apply it to this face, and then use a triangle dominant mesh. So that should be fine. We can generate this if we'd like. We're also going to add a sizing mesh, which will be an edge sizing of this circle. We're going to apply it to this edge right here, create a number of divisions of 250, and then make sure that our behavior is hard. We're going to also generate that. And then we are going to create a inflation. First, we are going to edit what our mesh element size is going to be. We're going to make sure that it's around 0.12. That ended up working best for me. Inflation, our geometry face that it'll be the actual face, and then our boundary scope will be this edge piece right here. We can apply it. Instead of smooth transition, we're going to do first layer thickness with our height being 0.03, I believe. Actually, what worked best for me was 0.003, and then our maximum layers we would make, I think, around 100. We are also going to adjust our edge size, since I also found that 300 worked best for me. Since we have all three of these things, we can now generate this mesh Might take a minute. Now that it is done generating, we can then see that our mesh looks like this. We can also make sure that we have enough elements, which we do, around 387,000. So that ends up working quite fine. We can then go back to our workshop, update this mesh, and then go straight into the setup where we have double precision and we can start that. Now that it is finally loading, once it pulls up our mesh, we will be able to simulate a couple flows. Actually, what we will do is go back and rename a couple of things. So now that we're back, the one thing that I forgot to mention is that we should name these sides, the left one being inlet, the right one being the outlet, which will be the pressure one, and the inlet will be a velocity inlet. And then the top and bottom being symmetries. This will allow the program to understand that these will be these. So then our circle will be our wall. And now that that is done, we can then update it here and close out this tab because this will always mess up. And then we can open up the setup again. Yes, load the new mesh. Double precision and start. Now that everything is loading in, we can actually get started. So what we want to do is first, we're simulating 3 different things. We're simulating inviscid flow, then viscous laminar flow, and then turbulent flow. So where we are starting is with our model. We should change this viscous to inviscid. Click OK. That works. Our material will be our air, where we change this to be just 1, a density of 1. Helps with calculations. Our boundary conditions, we just make sure that our inlet is exactly what we think it is. We're going to set this velocity inlet to be 5 meters per second. And then we make sure that the outlet is a pressure outlet, and then our wall should be our wall. So that makes sense. We also want to adjust how our methods are. So with our methods, we're gonna click simple. This allows simple and presto, and this allows the calculations to work more smoothly and go faster. So when we go to run our calculation, we're gonna do, let's say 300, and then initialize and calculate. And in a second, we'll see how all this goes. Okay. And now that our calculation is complete, I had already done it, we go to our contours, make a new one, and then we're able to see our static pressure contour. Here we can see that at this point is where we have the most pressure, as we can expect from the flow of the air to make contact here and not necessarily go straight through, and then we have our least pressure here. We can also then make our velocity contour. Do this order, save and display, and in those spots where we saw the least amount of pressure, we saw the most amount of velocity. It almost doubles. And where we saw the high pressure here is the least amount of velocity that we find. And that's how this viscid one looks, inviscid. And in order to find another value, you can go to reports, go to our forces, click on our wall, and we are going to be able to see in this window here our coefficients of pressure, which we find to be 0.0038. It should be very near 0. And one of the other things that we can find from the streamline is actually in this location we can also plot on the XY plot. We can find the pressure coefficient on the wall. Save and plot. And here for the InVisKid, we can see that there's a great pressure coefficient up here, and then it slowly slows down to this location and then goes back up. It's very symmetrical. This is the position on the cylinder. And we can also find from these plots is the velocity on the wall as well, and this should be the inverse of that. So here we see where that coefficient of that pressure coefficient was high, our velocity was very low, and then they were inversely related. So that is for that point. And one of the other last things that we need is we can plot our streamline function to see the streamlines around the cylinder. Here this takes a second to load, but once it does, we will be able to go right up here, create our streamline, and we will start from the inlet, create a lot of points, and then apply. This might take another second to load, but it will show us, yep, here is our velocity streamline. We see our greatest velocity right around the top of the cylinder and the bottom. And yeah, so that is one of the last things that we need from this part. And then on to simulate the laminar and then the turbulent. The best way to do this is to actually duplicate our InVisKid and change some results to get a greater Reynolds number and apply that for laminar and turbulent and change how the model is. We will change it from InVisKid to laminar and then again to turbulent, and this will give us different streamlines and different numbers for these values. And here duplicating it, we find it right here. We can change the setup. Our mesh is pretty good, so we can just utilize that. If our setup will load, again, double precision, select start. And once all of this loads, we will be able to change a few values. And so we will be using, once this loads, we'll be changing the model here from viscous to laminar, selecting OK, and then we will be adjusting our fluids to certain. And what ended up working best for us was this viscosity in order to get the proper Reynolds number. And then our inlet velocity stayed the same, yeah. And with this, we can initialize and calculate. Now that it is finished generating and iterating, we can then show again the contours that we needed. Same display, and then we can see that there is some sort of wake region that we find that we didn't see in the initial, in the previous plot and style. So here we can also see the velocity. We see this pattern, which is typical, and we can also find the other data sets that we really needed. So we can go to our XY plots and then plot the same. We want to plot our pressure coefficient to plot, close, and then we see this pattern. This is smoother and lower than, this will be smoother and lower than our turbulent flow simulation. And then we also want to see the velocity. This should be 0 due to the 0 shear on the cylinder assumption. Yep, right here. And then we will also find that one other with the forces and the drag coefficient. Find it on the wall, print, and then we find, yeah, these are actually quite high. Yep, there we go. And we should be able to find that our coefficients of pressure should be fairly close to 1. It's around 0.8624. And this total is 1.125. So that is what we get from this. We can also see that that was this. We got our plot, and then we can go on to our velocity fields, or the streamline fields. Well, we can find it the same way. And actually do it, we might be able to do it here. Then we go to results to find the streamline function, if it'll load in a second. Yep, we actually plotted it earlier, so this is how it should look. Goes around, comes like that. And then we can make our turbulent flow. So here we can go back to our setup to change it. Change a couple of things. Now with this loaded, we will change the model as well. We're going to change it back to normal K omega. Select OK. We will then change our material. Air, we are going to make it less viscous. Do 1 to the negative 6 power. Create. And our inlet velocity will be 5 as well. And this should basically be it. We will run this and see our results. And the calculation is done. We will open up our contours. We will create a velocity contour. We'll see this, and we actually see that we have a bunch of turbulence and right behind, causing some drag. We can also make the pressure contour here with everything, saving display. And then here we see that at these points we have the least amount of pressure, but we saw a greater velocity, and then a lot of pressure here up front. What we can also see from the report is the drag coefficient. We are going to, on the wall, print, and we'll see that this is lower than the laminar flow. And what we will also see from the plots is if we plot just the wall and the pressure coefficient, if we can zoom in on this, yeah, we will see that this increases quicker than the laminar flow, and it goes right above. We will actually see that in one of these graphs that this is the turbulent, it grows quicker than the laminar, and then this was the original in viscid. And so what we will also see is that the velocity on the wall should also be 0, which is indicative of the 0 shear stress rule on the on the surface of the cylinder. And then we can plot the uh, streamline. So here we're in the simulation, and here I ended up uploading the streamline myself. So here we can see that the streamline comes this way and this way to run. And there is more drag, but that is it, and that should be it for the project. Thank you for listening.